Our second section of notes today is focusing on, well, if this fusion is happening within a star, well, what kind of impacts does that have on the star long term? And our goal is to make a connection all the way to its lifespan, or really how long will that star exist? So as fusion occurs within these stars, what are the connections to other characteristics, getting ourselves to this idea of lifespan? So again, all of this is kind of stemming off our game that we've been playing, right? Thinking about how fusion is occurring within these stars because gravity is attracting these elements towards each other, and when they are attracted together, they can possibly fuse if the conditions are accurate, and that fusion creates a few things, right? Energy from the combination of the elements, as well as more massive elements. So as the elements combine, we're seeing new elements form, and they are more mass. They've got more stuff because I'm taking two or more things and combining them. So right now what we're thinking about here is our star relationships page. So this is our goal for part 2 of the notes. Starting here with this idea of what is gravity. Like we said, gravity is that attractive force between two objects, and of course those objects have to have some sort of mass, right? They have to be made of something in order to have material to be attracted together. Now we see gravity have an impact or change on the objects for a couple reasons. One, when objects are closer together. So the closer the objects are, the more gravity they are going to have. And also when the objects have a greater mass, right? When there is more stuff, what we end up seeing is an overall stronger force of gravity. And we've seen that happen here on Earth, right? We mentioned this last week. If something has more mass, like a giant refrigerator, gravity is pulling down on it with a greater force than something like a water bottle, right? The more stuff something has, the more of attractive force of gravity is being pulled on it. So just a real connection to stars, a real quick connection. You should, over here on the right-hand side, be able to label up the mass and gravity of each of these two stars. I think it'd be good actually to start over here, right? Which one has a high or low mass? Again, mass is referring to stuff, how much stuff it's made up of. So here we're looking at size to help us determine that. So go ahead and quick label which one has the higher mass, which one has the lower mass, and then we're also marking up gravity, which one has a high or low gravity because of that mass. Pause if you need extra time to fill that in, and then we'll get back to that left-hand side. Now, the more mass something has, the more gravity it has, and like we said, that star is pulling things towards each other for the force of gravity, or because of the force of gravity. Now, all these little hydrogen particles that are hanging out within a star, even though they're small, they do have a mass. So gravity is pulling them together, keeping them locked within this star. And like we said, the more mass a star has, the stronger that force is. So you've got this visual over there on the right-hand side. Just go ahead and label a couple of these arrows as gravity, right? Pulling those particles in towards the center. Now here's our big jump, is the more or less gravity we have, we want to know, well, how does that affect the rate of fusion, or really the amount of fusion that's happening within a star? So if a star is more massive and therefore has more gravity, the stronger the force is pulling these particles together. If you think about our game example from playing last week, our focus was swiping differently to represent the different levels of gravity. So if there's more gravity, well, I am then going to be doing more swiping, right? Creating a stronger pull for these elements to be attracted together and therefore allowing them to fuse at a much faster rate, or essentially a higher amount. This higher rate of fusion means not only can more elements combine, but also larger elements can combine. We've really started talking about these small elements like hydrogen with one particle or one proton and helium with two, but eventually we're talking about these more massive elements on the periodic table. So when there's a greater amount of gravity and a higher rate of fusion, that means there's more of a force for not only more elements to combine, but also larger ones as well. So pulling it into our last characteristic of lifespan of a star. Well, the faster the fusion happens in the star, the higher the rate, the more quickly that star will likely use its fuel up, right? Again, in the game, if we were swiping quickly, we were combining more elements, allowing for more new elements to be created through fusion, but also getting to these bigger elements at a faster rate. And as we were playing this game, we then also noticed with more fusion going on, there was a more likelihood that our star would die out, right? That we would burn through all of our allowable hydrogen and eventually, thought I could get there, eventually reach that point where our star ran out of fuel. So the faster the fusion happens, the more the star can burn through its energy resource and eventually run out. So the higher mass or the more mass the star has, the faster the fusion occurs and the faster it can use up its fuel, get itself to this empty tank level. Now, the analogy I always like to use with this is the semi versus the Mini Cooper car. I think we know that a semi has a much bigger gas tank, but it also takes more fuel to power that vehicle, right? It's going to get a much lower miles per gallon because it takes more energy for that semi to get going. So therefore, a semi is going to have a much higher rate of fusion, right? It needs to push or needs to grab its energy at a faster rate to keep going, and therefore it's going to burn through its gas tank a lot faster too. These bigger stars or more massive stars have a shorter lifespan. Whereas our little Mini Cooper over here, right, it doesn't take as much energy to fuel and run this little car, so it doesn't need as much energy initially to keep it going. It's got a lower rate of fusion because it's a smaller star. It takes less energy to power it, right? So its rate of fusion is opposite of the semi, a much lower or slower rate of fusion, and therefore a much longer lifespan. It's going to retain its hydrogen fuel for longer, burning for an overall longer time. So that brings us to our summary question here at the end. I'm going to switch back to our notes. You're just connecting all these things that we just went through: mass, gravity, rate of fusion, and lifespan. So go ahead, fill in the blanks with higher or lower, faster or slower, longer or shorter. So the same connections that we used over here on the side, you're going to go ahead and fill in those summary questions. So gravity is thinking about higher or lower. Rate of fusion Is it faster, meaning more fusion, or slower, meaning less fusion? And then lifespan, are we looking at a long or a short? So we're just combining all these details as we go. As always, reach out if you have any additional questions, but that's everything for your Part 2 star relationship notes. Make sure you've got left side blanks, right side diagrams labeled up, summary question complete, and you should go ahead and submit both of your pages.